Hi guys, and welcome to your first Chapter 23 statistics video. I apologize for getting this out to you on Saturday rather than the Thursday that I said I was going to get it out to you guys on. I spent from 8 till after 10 o'clock on Thursday trying to come up with the best way that I knew of to introduce this new concept. Not because the concept is challenging, did it take that long, but just because I don't have a mathematical justification for the use of this new model. But I mean, I guess then again, I didn't justify the use of the normal model in helping to describe distributions. At any rate, let's go ahead and take a look at, in 23, we're looking at two things. We're going to look at how we can build a confidence interval for a sample mean and also do hypothesis testing for a mean as well, for a population mean. And I want to start off by taking a look at the one use of the mean for a sampling distribution of a mean that we've seen so far. For instance, if I knew a population mean, that is to say, for instance, the height of all 17-year-old boys or the height of all 17-year-old girls across the United States, and I knew the standard deviation of those heights for either boys or girls as well, I have been able to say, we said this way back in Chapter 18, the expected value of a sample of, let's say if I'm collecting 100 boys, collecting, that sounds weird, if I'm taking a sample of 100 boys at a time or 100 girls at a time from the entire U.S. population, the expected value of that sample is just equal to the population mean of their heights. And hopefully you remember from either class or from the summary sheet that I gave you for all the sampling distributions we had seen in Unit 5, the standard deviation for the sample height of sample size 100 or sample size 10, whatever, would just be the population standard deviation over the square root of the sample size, the square root of n. Remember that, like we talked about way back in semester 1, I first brought this up, that when you have Greek letters, in this case mu, being the mean, and sigma being the standard deviation, those are all referring to population statistics. So those are things that are absolutely true for the population. Whereas x bar, that is a sample mean, that can vary from sample to sample of size 100 boys. Okay, well, so in 18 we said, well, if that's fine and good and all, then we can say, on average, the collections of 100 boys based upon their heights who are 17 years old would be centered right at the very same population mean. We'd expect collections of 100 to have, on average, the same height as the entire population of boys, and the standard deviation would have been sigma over the square root of n. So to either side we would have had sigma, or excuse me, mu plus sigma over n, square root of n, or mu minus sigma over the square root of n. So 64% of the time, you would have seen samples have the mean height between those two dotted lines, a standard deviation above and a standard deviation below the mean of the population. All right, well, notice here that in building this normal bell curve, we're building this curve based upon two things. Yes, every normal bell curve ever has two parameters. It's got a mean and it's got a standard deviation. But this particular bell curve depends upon both mu and sigma. Okay? So it depends upon, to talk about how sample means behave, we have to know both the population mean and we have to know the population standard deviation. On the other hand, if we want to talk about the sampling distribution of p hat, let's say we're given p, which could be the true population proportion of people who support Mitt Romney over President, or well, not formerly, over Obama, people who support Romney over Obama, to talk about how samples of, again, maybe size 100 of people in the United States might behave, the expected value of the sample proportion of 100 people collected at a time or sampled at a time from the population was just equal to the true population proportion, and the standard deviation of the sample proportion was equal to the square root of p q over n. All right, so we could have built a bell curve to represent how samples of size 100 behave in their support of Romney, centered on p. We expect samples of size 100 to mirror what the population is going to do on average, again, because we're talking about the mean. And to either side, you would have seen standard deviation above would have been P plus rad PQ over N, whatever that calculation would come out to. Standard deviation below would have been P minus rad PQ over N. So you would have seen 64% of the time samples of size 100 from the adult U.S. population would have varied between those upper and lower fences in their support of Mitt Romney over all the other presidential candidates. With this sampling distribution of sample proportions, unlike the sampling distributions of sample means that we just looked at, we have dependence upon a single statistic. Depends upon just P. Notice here that your mean for the sample proportions is at P, and the standard deviation also depends just upon P. Q, I mean, is not really a separate statistic because Q is always just 1 minus P, right? It's the complement of the population proportion. So, for the sampling distribution of P hat, our bell curve was really just built off of the two parameters, mean and standard deviation, just dependent upon one population statistic. Whereas for the sampling distribution of means, we had dependence upon both mu and sigma. Okay, so let's keep that in mind as we move forward. That's going to come back next slide. We have seen in the past, we saw that the confidence interval for one proportion was P hat plus or minus the z-score based upon the confidence level that we are using in our confidence interval times the standard error of that sample proportion, where the standard error of P hat was equal to the square root of P hat Q hat over N, right? So we could have built a bell curve to represent what this confidence interval is doing. Confidence intervals, remember, are trying to go from sample data to describe what population data is going to be doing. So this bell curve would have been centered upon P hat with standard errors of either side looking as follows. It would have been P hat plus square root of P hat Q hat all over N, or P hat minus the square root of P hat Q hat all over N. Okay. All right, here, this confidence interval for a single proportion depends only on, well, P hat. Just as the sampling distribution of sample proportions depended only on P, confidence interval just depends upon P hat, right? So, the normal bell curve, this tool right here that we've seen since way back in Chapter 6, was good to go in allowing us to talk about confidence intervals for one proportion because you only had one sample statistic that you were quote-unquote fudging with, that you were approximating P with to build this confidence interval. But if I look at a confidence interval for one mean, let's talk about what we think it would be. Well, if I wanted to use a sample mean, let's say, again, let's go back to the idea that I'm trying to describe how the heights of 17-year-old boys across the United States look, right? Well, to estimate that, based upon how we know that we set up the confidence interval for one proportion, we would expect it to look like whatever sample mean is. Let's say I collect, again, weird word to use here, that I sample 100 boys, age 17 rather, within Yorktown High School, and I see what their height is, and I would just then, based upon whatever confidence level I want, use the normal bell curve to get a z-score, multiply that by the standard error, which we would expect to be if the sampling distribution for a sample mean was sigma over radical n, and I don't have that population data, I don't have the true population standard deviation, I would expect the standard error here to just be S. Recall that S stands for the sample standard deviation. I would expect my confidence interval to be based upon the sample standard deviation of the 100 boys that I'm sampling from Yorktown High School all over the square root of n. So this would look like I would have a confidence interval centered on x bar. To either side, we would see x bar plus s over radical n, the sample standard deviation over radical n, and I would have x bar minus s over square root of n. So in either case, I would have a 64% confidence interval to that one standard error above and below the sample mean, right? Okay, but, last slide we said the sampling distribution of x bar depended upon two statistics, sampling distribution of sample proportion depended only upon one. That's actually going to come back to haunt us right here. This, if we were to build a confidence interval for one mean here, using the normal bell curve in this way, we would get data that would be wrong because this bell curve depends on both x bar and s. Okay, that's a problem because the sample mean and the sample standard deviation can vary both let's talk about it individually. X bar can vary a lot from sample to sample. I can expect that 100 boys looking at their heights on average at a time can be hugely different from each sample size of 100 among the U.S. population. Similarly with S, similarly with the sample standard deviation. It could be the case that among my 100 boys, 50 of them are all like right at 6'2", 50 of them are all at like 5'6". I mean, that's not likely, but it is possible. I could have, on the other hand, and so that would, the first case would create a lot of standard deviation, a greater standard deviation. On the other hand, I could have everyone right at 6 foot. So because this confidence interval that we would try to build here using the bell curve depends upon two different sample statistics instead of only one. Long story short, the normal bell curve does not work for the confidence interval for one mean. But the good news is that a distribution that looks almost identical to the normal bell curve and is used in almost the same exact way does work. And that distribution is called the t-distribution. The t-distribution is, I guess, a bit of a misnomer because the t-distribution is a lot of distributions. They all look like the normal bell curve. You see in this picture here 4 different t-distributions. Notice that they all have that sort of unimodal shape. They all have a central peak. Notice that they are all symmetric, again, just like the normal bell curve. If we wanted to be able to build a confidence interval for a sample or for a mean of a population from a sample mean, we can do it with this t-distribution, which has fatter hips here on the left and the right sides and a narrower central peak. If we were to plot the normal bell curve over these t-distributions, it would look something like this. It would be awfully low here at the center, then come up steeply, and then sweep back down narrowly. So in black, I added what is more or less the normal bell curve overlaid with the t-distributions. The t-distributions depend upon, the one that we would use to solve a problem depends upon the sample size that we have in the problem. So it's all about context as ever with statistics. If you have a small sample size, you're going to have, let's say you want to estimate, I know this is crazy, let's say you want to estimate the average height for 17-year-old boys in the United States based upon a sample size of just 2, right in here. So your degrees of freedom would be equal to 1. That would mean that you would work with the t-distribution right here that I am trying to point out for you at the moment, which has the shortest central peak and the widest hips. Those wider hips allow for more variability in the answers that we would obtain. When you increase the sample size, let's say if instead of only using 2 boys age 17 to estimate the true population mean of heights across the U.S. Population, let's say you used a sample size of 4, all of a sudden, now you would be working with this curve right here that's already outlined in red for you, which has a sharper central peak and it has narrower hips. That sharper central peak means that you have a more accurate estimate of the true population mean of boys' heights age 17. Those narrower hips allow for less variability in the answers you would get. So the t-distribution, because it's got those flared hips, the narrower peak, that allows for more variability in the answers that we would obtain when building a confidence interval for a mean or using a hypothesis test for a mean than the normal bell curve would use. Okay, so nothing else in terms of the parameters other than the fact that, yes, we do have to keep track of the degrees of freedom for the t-distribution that we're using. Degrees of freedom only comes up with reference to which t-distribution we are using to solve the problem. But other than that, it's not used for any other calculations. Expected value of the sample mean would just be equal to whatever sample mean that we obtain. And the standard error of the sample mean would be equal to, let me find that calculation here, would be equal to S over the square root of n. So now we're getting away with these 2 parameters for the t-distribution depending upon 2 different sample statistics. Whereas with the normal bell curve, the normal bell curve is not flexible enough to allow us to do that. Again, when you use 2 different sample statistics, variability in your answer goes up, rather than if you only used 1 sample statistic. Because obviously samples won't behave exactly like the population data. If we'd been able to use population mean and population standard deviation, a t-distribution would not be necessary. All right, so with any distribution, with the normal bell curves we have used in the past, we need to check some conditions here to make sure that we are good to go with the t-distribution for confidence intervals or for hypothesis testing of means. First thing that we will check is the same as any other condition ever. We're going to check the randomization condition. Do the data arise from a random sample or suitably random experiment? 10% condition. Is our sample size less than or equal to 10% of the population? So both of those are kind of old hat. Nearly normal condition is the new guy here. In this one we check as follows. We are looking to see, are the data in our sample from a unimodal and symmetric distribution? Notice again, if I scroll back up here, that the t-distribution is both unimodal and symmetric. One central peak, and it's the same both to the left and to the right of that central peak. So how do we check this? We build a histogram. However, for a sample size that we are working with that is less than 15, it is very important that the histogram we build to check this nearly normal condition, this new condition that we have, it's very important that the histogram be both unimodal and symmetric. If your sample size is greater than 15 but less than 41, so you're talking 16 to 40, if you've got a sample size within that window, the histogram of the sample does not necessarily have to be symmetric, but it does have to be unimodal. So you need at least one central peak, but it's okay if you've got a little bit of skewedness or some outlier issues. If you've got a sample size that is greater than 40, go ahead and make a histogram to check the nearly normal condition, but, and that's more for the sake of repetition, so you remember to do that when you check the nearly normal condition. But ultimately that histogram doesn't really affect whether or not you will not qualify based upon this nearly normal condition to use the t-distribution to answer a question about a confidence interval or hypothesis test for means. So sample size greater than 40, make the histogram, but you're good to go. The data doesn't really need to be unimodal and symmetric. All right. To explain this, I know I've said a lot of stuff that's probably a little bit confusing. The t-distribution, again, basically is the normal bell curve. We've got a couple of new tools that we will talk about further in class on your calculator that can like instead of an inverse norm, there's an inverse t, but it functions similarly. Instead of a normal CDF, there's a t-CDF, but it functions similarly. So really this t-distribution, think of it as a normal bell curve, only it's a special type of normal bell curve that only applies to these sample means. Let's check out a problem together to sort of gear us up for what we're going to do in the rest of 23. Trip Hammer Road is a busy street that passes through a residential neighborhood. Residents there are concerned that vehicles traveling on Trip Hammer often exceed the posted speed limit of 30 miles per hour. The local police sometimes place a radar speed detector by the side of the road. As the vehicle approaches, this detector displays the vehicle's speed to its driver. The police hope that drivers will slow down if they are reminded of their speed. We want to build a 90% confidence interval for the mean speed of all vehicles traveling on Trip Hammer Road from the data collected below. So we've got a total of, you've got 2, 4, 6, 8 columns here and 3 rows. So 24 minus 1 cell is empty of data. So 23 different data entries of vehicles driving down Trip Hammer Road. We're trying to, from a confidence interval, talk about what we expect the mean speed of drivers on Trip Hammer Road to be. And that'll allow us to make conclusions about whether or not you should up the speed limit, if you should have more cops in the area, that sort of thing. All right, so from this data, let's go ahead and, to build this confidence interval, let's check the conditions, 2 of which, again, are old hat from the past. And then the nearly normal condition is new for sampling distributions. Conditions here, randomization. Actually, with how this data is being collected, there's nothing to suggest that we have random data whatsoever. So this is really not met, but we will assume the sample is reasonably random. Okay, so just as in the past, unless you have, we were not told that the data was collected randomly. In all likelihood, with how these speed traps are set up, I doubt that there's any way this is really being met. But we're being asked to build a confidence interval, so we're going to state that we have a caveat here. We don't believe that this is met in this first line, but we're pressing forward anyway. All right, so randomization knocked out of the way here. Next up, 10% condition. This one I think we can safely assume, and that is because 23 cars and the speed limits associated with those 23 cars has got to be less than 10% of all cars on Trip Hammer Road. And then the last condition, let's check the nearly normal condition. Yes, because we need to build a histogram of the data. This takes a little bit of time to check, but I like that it's good practice for how we use our graphing calculators to build histograms. That's an important tool to be able to be adept with come AP exam time. Nearly normal condition. Okay. Let's check it out. I have preloaded the 23 different data entries into my TI-84 Plus. So if I go into Stat, let's turn the thing on. If I go into Stat, Edit, you've got the 23 data entries, and I've double and triple checked those to make sure that they line up with the Excel or the table entries that you have in the notes. Those are the same. So remember, to build a histogram from this L1 list of data, we're going to go second stat plot, make sure that we've got a plot that's on. We do in the first case. We'll enter into that. I've already chosen a histogram here. The X list is correct. That's L1. Frequency is 1. Remember, histogram keeps track of one variable's worth or one characteristics worth of numerical data at a time. So from here, to get your histogram, remember we go zoom. Whoop, let's quit out of that. Let's go zoom stat, which is zoom 9. Enter that, and there's your histogram. So from the look of this, yes, we did meet the unimodality and symmetry conditions both. We're going to write those down first. Both unimodality and symmetry are met from the histogram. Okay, that's the first thing we want to do. Second, that's not really enough. It's not okay to say that they were met. We need to reproduce the histogram in our paper here, and that's really where the extra time comes in. So we're going to draw this out, this histogram out. It shouldn't take us too terribly long. To do that, remember that by tracing, you can keep track of each of the 7 bins in this case in the histogram. The min tells you the lower, what's the word I'm looking for? The lowest possible data value that you can have in that particular bin. So our first bin ranges from 21 to 23.83 repeating is 23 and 5/6. The next bin would go from 23 and 5/6 to 26 and 2/3, etc., etc. And then the n for each of these bins is the count for that particular bin. Okay, so hopefully that's old hat for you guys. Let me reproduce that in, let me minimize this real quick. Let me reproduce that in the notebook here. So, I've drawn this once before. This is our histogram for nearly normal condition. We've got our count over here, and that's going to range from 1 to 6. 1, 2, 3, 4, 5, 6. With, let me scroll down just a tad. We have 21 far left. We've got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. All right. First bin at 21 to 23 and 5/6 had a count of 1. And I'm going to number each other hash mark. So this is 29 and a half. Next after that would be 35 and a 6. You guys are welcome to do this too. If you want, when you're numbering your quantitative data on your x-axis, your horizontal axis, go ahead and skip if you want for the sake of room. 40 and 5/6 is on the high end. Okay, counts for each of those bins were at 2. Then we jump way up to 6. Then we, wow, that one's a little wonky. Then we go to 5. Then we are at 3. Then we're at 1. Okay, all right. So there we go. We've got our evidence now that the 23 data entries are, when you make a histogram of them, from a unimodal and symmetric distribution. Okay, so conditions are knocked out. Let's go ahead and mention what our model is here. This is a new model because we have a new distribution, and we're talking about X bar in a new way. Our model is a one-sample T distribution for a mean, or for the mean, whatever. Okay, so the model's knocked out. Let's go ahead and do the mechanics real quick. Let me draw the T distribution, which will look, again, a heck of a lot like the bell curve. So this is our mechanics. This is the guts of the confidence interval problem, where we're trying to estimate the true speed, average speed of people driving down Trip Hammer Road. We've got a T distribution here, which I'm going to draw just like a bell curve, and then mention the number of degrees of freedom, because remember, the T distribution varies from sample to sample. That the degrees of freedom really determines which T distribution we're talking about. It's a whole family of distributions. Degrees of freedom here equal to n-1, sample size -1. If we had 23 in our sample size, we're looking at a degrees of freedom for this particular distribution of 22. The expected value of the mean speed, mean sample speed of cars driving down this road would be equal to, let's see, that's not one of it's right. The confidence interval looks like the following. Y bar, centered on the mean, sample mean that is, plus or minus, instead of a z-score, because we're talking about a T distribution, we talk about a t-score. Not a big difference there. The only thing that we'll want to do differently when we write a t-score instead of a z-score is put a little subscript here of 22, which is the number of degrees of freedom associated with the model, okay? So we've got a t-score that we're going to find here shortly based upon the 90% confidence, which will give us this t-score, times, just as we've used confidence intervals in the past, times the standard error of y bar. Okay, so this guy right here will estimate that true population mean speed of cars driving down Trip Hammer Road. Now, how do I get y bar, the first thing in the confidence interval? Well, if you remember, we have used one variable stats in the past to give us r, the correlation coefficient, to give us r squared, to give us standard deviation of y, standard deviation of x, to give us standard deviation of lots of things. We can get y bar here just by going one variable stats on the list L1, and when you do that, you get 31 plus or minus. Well, how do we get this t-score? Okay, so this bell curve to represent our confidence interval is centered on the sample mean speed of 31, and we want a 90% confidence interval. So just like we have done with inverse norm, if we want a 90% confidence interval, instead of inverse norm, we are going to use inverse t, specifying. Note that if we want a 90% confidence interval centered on that sample mean of 31, we are excluding 5%. Let me write it like this: 5% to the left and to the right of this t distribution from our confidence interval. So we're going to say inverse t of 0.95 on this upper dotted fence, because remember that inverse t, well, don't remember inverse t, but remember inverse norm tells you a z-score corresponding to the percent of the data less than that value. Inverse t works similarly. We're going to get a t-score instead of a z-score based upon the percent of the data, percent of the t bell curve here less than that value. So 0.95 comma 22, because remember there are a whole host of t distributions. We need to specify which t distribution it is based upon the sample size. And when you do that, inverse t of 0.95 comma 22, you get 1.717. Okay, so we've got 31 plus or minus 1.717. Now for our standard error. Standard error calculation, I'll put right here. Standard error is of y bar is equal to s over the square root of n, which is equal to how do we get s? Well, we get s the same way we got y bar. You use one variable stats on the list L1, L1 having your 23 different speeds of the cars driving down Trip Hammer Road. So s is equal to 4.25. Radical n is the square root of 23. So your standard error of this t distribution is going to be 0.886. Okay, so we've got enough to fill this out. Plus or minus 1.717 times 0.886. If we want to simplify this, and the easiest way to understand using sort of that coordinate pair style notation, we could say that our 90% confidence interval for the true mean speed of cars driving down Trip Hammer Road would be between 29.479 and 35.521. Okay? They wanted us to build a confidence interval. As I normally do, this is not necessarily part of the context of the problem. This wasn't asked of us, but let's interpret that interval now. So last little bit here in conclusion. Let's wrap this up. We would say I or we are 90%, not 95. I'm thinking of the value I got right here. I am 90% confident that the interval from approximately 29.5 to 32.5 miles per hour contains the true mean speed of all cars on Trip Hammer Road. Okay, all right. So let me wrap this up by saying just a couple of things here. With a confidence interval in that range, a 90% confidence interval, we don't necessarily know that the average speed of drivers on this road is a speeding speed, do we? Because 30 is contained in that confidence interval. So it's totally possible that on average, people are driving right at the speed limit on Trip Hammer Road. Now, obviously, that doesn't mean that people are speeding, because the only way you can have an average of 30 is if literally everyone in the entire population is driving 30, or if some people are speeding and some people are going below that speed. All right, so there's the first thing I want to mention about the context of this problem. Second thing is this. Let me just look back here real quick. T-distributions. When do you use them? Well, you only use a t-distribution to talk about sample means in some context. It could be for hypothesis testing, it could be for sampling distributions, it could be for a confidence interval. You only use a t-distribution for sample means when you do not have these two things right here, circled in the blue. If you do not have the true mean and the true standard deviation from your quantitative population, think back to when we were talking about 17-year-old boys and the heights of them across the U.S., then you do not use a t-distribution. You could get away with, if you had the true mean and the true standard deviation, you could get away with a bell curve. If you don't have the true mean and the true standard deviation, you have to use a t-distribution. In general, expect to use a t-distribution. And again, the only new thing with t-distributions, yes, they are fatter to either end, and they are a little bit more blunt in the center. They don't have quite the central peak that the normal bell curve has, but the only new thing you need to keep track of with reference to them is the degrees of freedom when you write out the t-distribution. So just as I did in the sample here, with any problem you use a t-distribution on, write out the degrees of freedom for that problem. Everything else about this problem hopefully looks similar to how you would have constructed a confidence interval for a single proportion. Confidence interval for a single mean and confidence interval for a single proportion are kind of mirror images of each other. Just you're using t-distribution for mean, normal bell curve for sample proportion. That's what I've got for you guys. Thanks for your attention. I will see you Monday.